All right. Hello, everyone. Thanks for joining us for the QRISE speaker series, our second guest lecture by Professor Jesse Berezovsky. Professor Berezovsky is a professor in the physics department at Case Western Reserve University. His lab designs and creates hybrid systems for controlling coherent quantum spin states in scalable room temperature platforms. He also studies applications of statistical mechanics to music theory, composition, and performance. He received his PhD from UC Santa Barbara in 2007, and before joining the Case faculty in 2010, he worked as a postdoc researcher at Harvard, imaging quantum transport in graphene. Professor Berezovsky has co-authored numerous articles in journals including Science and Nature Physics, as well as a book on the optical properties of electron spins in quantum dots. Well, now I'll hand it over to you, Dr. Berezovsky.
Thanks, Caden, for introducing me, and thanks for inviting me to speak today. So I'm going to tell you a little bit about this platform for creating quantum bits that's a so-called spin-based defect qubits, in particular in diamond. So this is a platform that is not as advanced towards building quantum hardware as, say, superconducting qubits or ion traps or things like that. But I hope to show you that it has promise as a qubit both for near-term applications like quantum sensing, and in the future might lead to possibly a competitive platform for computing applications as well. So first, let me there we go. Sort of remind you of how quantum spin behaves. And so I'm assuming the audience has some, interest in quantum computing, and so you've probably thought about qubit states before. And the spin of an electron, a spin 1/2, forms by itself a very natural qubit state because it has two orthogonal eigenstates, which we often call up and down. Let me see if we can get a pointer. I don't know. Can you see the cursor? No.
Yes, we can see the cursor.
Oh, you can. Okay, good. So we have two orthogonal states up and down, and we can construct a general spin state as a superposition of those with real coefficients A and B and phase phi. So as you may be familiar with from the general case of qubits, the two coefficients have to be normalized. So their squares add up to 1, which we can, sort of picture in the block sphere picture where this is an angle, polar angle theta over 2. And so we can draw the spin state on the block sphere like so, where we have our up and down spin states at the north and south pole, superpositions of up and down with equal amplitude around the equator, and a general state of the spin indicated by the arrow pointing to the surface of the block sphere. And so you can use this representation for any sort of qubit. For a spin 1/2, it kind of has a particularly intuitive understanding. And if you think of a spin as a magnetic moment, classically, that points in some direction in three-dimensional space, the arrow on the block sphere really corresponds to the direction of that magnetic moment is pointing in. And so if you know how a magnetic moment behaves, you kind of already know how a quantum state of a spin 1/2 particle behaves. So one thing that happens is if you apply a magnetic field, that gives you a difference in energy between up and down. If you have a magnetic field along that up and down direction, then you have an energy difference between those two states. And if you start with some state on the block sphere, then what happens both to a classical magnetic moment and to a spin 1/2 state on the block sphere, it starts processing around the axis defined by that magnetic field. The frequency of that precession depends on the energy splitting and hence the magnetic field. Okay. So how do we put this to use? So as I was alluding to, if you have these spin qubits, there's a very sort of near-term application for them, which is to use them as sensors. And so as a sort of an illustration of how that works, say we have our two spin states up and down that now I'm calling 0 and 1. and you prepare them in a superposition of equal up and down. And then if you have this energy difference between the two and you let the state evolve in time, then you get this, as I was saying, this oscillation, this precession in time at a frequency omega given by the energy difference. And if your state remains coherent for a long time, has a long enough coherence time, it can undergo many, many oscillations. Now, the idea behind a sensor is that if there's anything in the environment that perturbs that frequency, so if that frequency changes by a little bit, then it's just a very slight change in this coherent precession frequency. But if the coherence time is long enough, that could result in a very large change in the spin state after enough time has elapsed. So if you measure at the end, you get a large state change in the measured spin state for just a small change in the environment. And so what can perturb this energy splitting? So what can you measure with a single spin? You can measure magnetic field, of course. Magnetic field is the most natural thing that controls this splitting of the spin states. But there can be other effects like spin orbit coupling that mean that spin splitting is also sensitive to electric fields, temperature dependence, strain of a crystal hosting this spin. There can be orientation dependence, again, due to the crystal structure that the spin finds itself in. Similarly, pressure is related to strain. And a nice thing is that if you have a single electron spin that's confined to a very small size, you can sense all these things with extremely high resolution, spatial resolution. And so we'll come back to some of that in a minute. So in terms of what you could use these sensors for, this is actually a pretty old plot at this point from this paper from 2008. But even then, you can see they're comparing one of these spin sensors that's going to be in this diamond platform I'll tell you about to various other kinds of sensors that can detect magnetic fields. And on this axis here, we have a magnetic field sensitivity. So how small of a magnetic field can you detect? And you see that the diamond sensor is competitive with some of the other sensors, but not the best. The squid sensors down here are the best by some orders of magnitude. But on this axis here, we have spatial resolution. And you see that here, the single spin sensor is the best of all of them because it's just this, single electron or a few electrons bound to a few atoms. And so there's two different axes. And why do we care about those two axes? Well, of course, spatial resolution is sometimes useful for various things, but the two actually go hand in hand because say the thing you're trying to sense is itself very small. Like say you're trying to sense the field, the magnetic field generated by the magnetic dipole of a single electron, or for that matter, the dipole moment of a single proton. So a proton is and an electron are both spin 1/2 particles that generate a very small magnetic field around them. And if you want to measure that field, there's sort of two things you could try to improve. You could try to detect smaller and smaller fields going this way. But if you can bring your sensor closer to that proton or that electron, the field you're trying to sense will get stronger because it's a dipole field. So it falls off like 1/r². So you really gain a lot by getting closer to the thing you're trying to sense. And these squid sensors are very large, well, relatively speaking, maybe microns. And so there's only so close you can get. You see, that's why the spatial resolution is sort of limited at the micron scale here. But since the diamond sensor is so small, what really matters is where these sort of diagonal lines that you can cross. And so here they're sort of arguing that these diamond spin sensors are in this range where they can actually detect maybe even the dipole field from a single proton. So this raises the question of why would you want to detect the magnetic field from a single proton? Well, it's a very useful thing to be able to do to detect the dipole field from protons, because that's what you do in an MRI machine. An MRI machine detects, the protons of molecules in your body, often, in water molecules, and it's detecting the spin of the protons in the hydrogen atoms or other atoms. Now, the MRI machine, of course, it has spatial resolution, but you're measuring many, many protons at once, 10 to the 20, 10 to the 23, whatever. And so the idea here is, could you scale this down to the ultimate limit and image, say, a complicated biomolecule like this at the level of mapping out where the individual protons are using one of these quantum spin sensors. And that's sort of the dream, and it's not quite there yet, but people are pushing the limits further and further down and measuring smaller and smaller, sort of a handful of protons, and can really sense what's going on in, say, a molecule at the nanoscale. Okay, so like I said, these kinds of applications actually exist today. And I'll tell you about more sort of things we're doing in this area. But looking towards the future, you could think of using these spins as qubits in a computing system as well. And so I probably don't need to belabor the point of quantum computing here, but the idea is that you would use your spins as a qubit. And classically, the spins could be in one of two states, and you could think of them as regular bits, where you would place them in some particular set of up and down or ones and zeros. But if you have qubits, then you put them in a superposition of all those possible inputs, and you unlock the sort of exponential power of quantum computing. And that's all I'm going to say about quantum computing, because that's not really the focus of this talk. But the idea is that I'll sort of go over some of what we can do and what we can't do with these qubits right now. But one sort of takeaway point is that the fact that these things have immediate application as sensors means that there's a reason to work on them and a reason to optimize them and learn how to control them and build devices with them that work more and more efficiently and could help us overcome the barriers that we need to overcome to get to where we can build scalable computing systems with them. Okay, so what do we need to be able to do to harness these quantum effects with these spins? Okay, so these are sort of like the DiVincenzo criteria, if you're familiar with these, particularly in the case of spin qubits, though. So first, you need to be able to initialize the spin state into some particular state. You need to be able to control that individual spin state coherently to put it into an arbitrary superposition state. You need to be able to controllably couple two spin states, so you can create entangled states between multiple qubits. You need to be able to measure the spin state of all the different qubits. And just to specify this clearly, you need to be able to do all these things in an addressable way to measure one of the qubits that you're trying to measure, or to manipulate one that you're trying to measure, or couple a particular pair of them that you're trying to couple. So you have to have addressability, which is sometimes particularly difficult when things are scaled down to nanometer dimensions. Okay, so we'll come back to this and I'll show you the particular platform we're looking at, the nitrogen vacancy, defect, and diamond, and return to what of these things we can do and what of them we can't do. Okay, so the nitrogen vacancy, defect, and diamond is, so like I said, it's a defect in a diamond lattice. So a diamond lattice is shown here of lattice of carbon atoms. And here we have this defect where one of the carbon atoms is replaced by a nitrogen atom, and a neighboring latticite is vacant. So that's the N and the V, making up an NV defect. And because the nitrogen has a different number of valence electrons at carbon, and of course the vacancy is a lack of any valence electrons, there are electrons bound to this site. Five extra electrons there from the N and the V. And then the defect often becomes charged due to defects that occurred, or electrons that are available due to other defects in the system. And that's the state we're interested in, is this negatively charged defect. So 6 electrons. And it turns out that when you put 6 electrons in this confined environment of this particular, orbital structure of these in this lattice, you get a ground state where the spins align to form spin 1, total spin. And that's going to be the qubit. So the advantages of this system are it's a solid state platform, so you can get a diamond chip. We can grow synthetic diamond on a chip. You can buy them commercially. They have pretty good performance at room temperature. You can get coherence time of a single qubit longer than a second with maybe 10 nanosecond time gate times. And so that's extremely good. I mean, that's much better than either superconducting qubits or ion traps, even at low temperature. You can initialize them optically and read them and manipulate them using microwave spin resonance. I already mentioned the long coherence time, I guess. You can measure them optically. So they're very handy to integrate into optical systems. And like I said, they have this nanometer size scale, which means for sensing applications, very high spatial resolution. For prospects of scaling it up, you could pack a lot of them into a very small size. So here's the challenges, though. Okay, these are the big challenges. It's hard to couple two of them together. It's often a trade-off you have. It's sort of a catch-22. It has a very long coherence time because it doesn't interact with things very much, which means it also doesn't interact with other defect spins very much. And that's what you need to scale up a quantum device that relies on entanglement. It's also difficult that we're talking about nanoscale resolution, nanoscale separation. But if you're measuring things optically, you can only focus a laser down to maybe a few hundred nanometers. And so that if you can't rely on that for your spatial resolution. So those are problems I'll talk about a little bit more and how we might overcome them in a few minutes. First, how does this a little more detail on how the NV defect works as a qubit and how we can control it and manipulate it. Okay, so diamond is you're going to think of it either as an insulator or as a very wide bandgap semiconductor. So the valence band of diamond, which is where up to where the electrons are filled, is separated from the conduction band of empty states by about 5.5 electron volts, as compared to something more like 1.5 for silicon. And the defect creates has its electrons bound to this defect have their ground state somewhere kind of near the middle of this gap. And what that means is that these states of the electrons in the defect are pretty far in energy from both the valence band and the conduction band, and so they're well isolated. It's almost like you're holding this defect in a vacuum, almost like an ultra-high vacuum. Like when you have an ion trap, you have an atom, and you need to have an ultra-high vacuum because you can't have any other atoms around, colliding with the atom of interest or interacting with it that you don't want. In this case, if you make sufficiently high purity diamond, you get that sort of for free on a chip. So like I was saying, the ground state of the spin is a spin 1. And so if you remember, total spin 1 has 3 spin sublevels, or 3 projections of the spin. M sub s equals 0 or plus or minus 1. And it just and so that's it. So happens that a spin 1 with those it can be in a singlet or a triplet state. You may recall this. Triplet state has total spin 1, and these 3 sublevels. The singlet state has total spin 0 and only ms equals 0. So in this case, the ground state is the triplet with spin 1, and you see I've drawn it with this splitting between ms equals 0 and ms equals plus or minus 1. And that's a built-in splitting due to the crystal structure. And so it's like, because you have this kind of asymmetrical structure with the N and the V along some particular axis, you get almost like a built-in effective magnetic field, well, sort of, that gives you this splitting that in frequency units is about 2.87 gigahertz. So like I said, we have the triplet state, which is the lowest energy state. You also can have the singlet arrangement of spins, which is higher energy. I drew it over here. And these are both, so these are the spin states. You also have the orbital states. The states, in an atom, the orbital states, you have your S, you have your N equals 1, N equals 2, N equals 3, or SP, the orbitals. So this is the ground state, the lowest energy orbital state. We can go to the next highest orbital state, drawn here, almost 2 electron volts up, so still nicely within this gap. And it also, so this is all, the triplet is the next lowest, the next one also has this triplet and singlet states. So the next lowest one is also a triplet here. And so looking at these energy scales, this scale of about 2 electron volts is very convenient because that's sort of like the energy of a visible photon, particularly like a red photon. And so that makes this platform easily accessible for optical excitation and also for fluorescence in the visible range. And this frequency scale here of around 3 gigahertz means that it's very convenient frequency to drive microwave transitions. And so those are the tools we'll use to deal with this spin state. So first I'll tell you about the sort of optical properties. So here's this diagram again, where we have our triplet ground state, our triplet excited state, and our lower energy singlet state. So what we can do is we can shine green light on this defect, and it excites an electron. Say an electron starts out in this ms equals 0 state. It will excite it, the green light will excite it into some higher energy state that's not drawn here. It will very quickly relax down to this ms equals 0 state by emitting phonons. And so now you've excited from the ms equals 0 ground state to ms equals 0 excited state. The key thing there is that the spin state stays the same when you do this. It goes from 0 to 0. And then what happens next is that it will pretty rapidly, within tens of nanoseconds, decay by emitting a red photon back down to the ground state. So that's fluorescence, is red light that you can measure when that happens. Now, if instead of starting in the ms equals 0, you started in the ms equals, say, +1 state and did the same thing, you would excite in the same way, and it would drop down here, but wind up, again, conserving the spin into the ms equals +1 excited state, and then drop down, back down, again, conserving the spin, emitting a red photon. Okay. Now here's where it gets a little more interesting, is that it can make a transition from the triplet state to this singlet state. It doesn't happen very often, maybe some few percent of the time. And it's more likely that that transition occurs from the ±1 state to this singlet. So that's called an intersystem crossing, due to chemists who like to give things obscure names. But it goes from the triplet state to the singlet state via this non-radiative process, and more likely to happen from the ±1 state than from the 0 state. And so now you see the spin is not conserved, it's switched. It sits in the ms equals 0 state for a while, and then will decay, again, non-radiatively back down to the 0 state. And what you notice with this transition is now the spin has been flipped. We started in the ms equals +1, we got excited up here, but then we returned back down to the 0 state. And so that's kind of, this is sort of the key thing. So that's what I just said, is that you excite with green light, and the most likely thing that happens is red light is emitted and the spin state is unchanged after the process is done. But occasionally what happens is that if you're in the ms equals ±1 state to start, you wind up at the end of the day in the ms equals 0 state. So it does two things. One of that is a mechanism for doing the initialization of your qubit. One of the things we need to be able to do with a qubit. So that means that if you start off in the ms equals 0 state and shine green light, continuously, excite it many times, it'll just stay in the 0 state. But if you start off in the ±1 state and shine many green photons, repeat this process over and over again, eventually it's going to go through this process and you'll end up in the 0 state. So both of those roads lead to being in the 0 state, giving you a fairly high probability of eventually ending up in that 0 state. We all can use the same process for reading out the spin state. So because the 0 state, if the spin is in the 0 state, where you shine green light again, what almost always happens is you just get a photon rapidly out as it decays back down. You get a high rate of red photons emitted. But if you're in the ±1 state, you still get red photons emitted because it is still likely that it will drop straight back down. But it has this chance of getting stuck over here. which means you'll get a reduced rate of emission if you're coming from the ±1 state. So by shining green light and measuring the intensity of the red fluorescence, you can detect what spin state the system is in. Another one of the things we need to be able to do for a qubit. All right, how about control of the qubit state? So here's our 0 and ±1 states split by this built-in splitting. Like I said, if we put a magnetic field on, that splits our spin states. I was talking about spin 1/2 before, but it's similar for spin 1. Now we have a splitting between the +1 and -1 that's proportional to the magnetic field along the NV axis. And we can now, if you want to think of this as a qubit, it's kind of funny because there's 3 levels, but you could just pick 2 of them to be the qubit states. So we could pick the ms equals 0 and ms equals +1, for example, to be the states at the qubit, and we can think about this in the picture of the block sphere. Now, if we want to manipulate the spin state, we've initialized it into the 0 state. You want to manipulate it, the idea is to use spin resonance. I'll go over this kind of quickly because you may have seen this before in other contexts, because that's usually how qubits are manipulated. In short, the idea is that, if you start it there, the spin is processing around. More useful to think of this in a rotating reference frame. So here I'm spinning the blocks here, keeping the spin state the same, with some small magnetic field we're applying at some arbitrary frequency, and that has no effect on the spin state because it's a very small field that's oscillating here. It doesn't really do anything to the spin state unless we put that magnetic field equal to this precession frequency, so that now in the rotating frame, this small field we're applying is constant. And then that causes an overall manipulation of the spin state around the block sphere, and we can turn that on for as long as we want and do arbitrary manipulations of the spin. Okay, so to sum that all up, here's the picture again. Here's what we can do. We can initialize the spin state by illuminating with green light. It's actually very easy. A laser pointer will do it. You can control the spin state using microwave spin resonance at this relatively easy frequency of around 3 gigahertz. You can detect the spin state by measuring the emission rate of the fluorescence. But other things we need to do, like coupling the spin states and addressing the spin states with nanoscale resolution, are still quite difficult to do. Like if we're initializing and measuring by focusing a laser down onto one of these defects, we don't have nanoscale resolution. So I'll tell you now about sort of where the state of these things are. These are the sort of roadblocks that need to be overcome. So coupling and entangling NV spins has been accomplished in, I think, 2 different ways. So I'll tell you about how that's done. So the first mechanism for coupling 2 NV spins is by sort of a photon-mediated process. And so sort of loosely speaking here, the idea is that particularly if you cool the system down to sort of Kelvin scale temperatures, so you don't need to be as cold as a dilution refrigerator, millikelvin, but a few Kelvin is okay. You can have it so that when this fluorescence occurs and the spin emits a photon, that the emission of the photon is entangled with the spin state. So I've indicated that by the sort of, drawing this line around them. So this spin has emitted a photon and the 2 are entangled. And then we have another spin over here where it has also emitted a photon and those 2 are entangled. And so you may have seen this idea before. It's sort of like it's like this idea of entanglement swapping, where you can perform a joint measurement on these 2 photons and it will entangle the 2 spins. So that's used in things like the idea of a quantum repeater, where instead of a spin and a photon, it would be like 2 entangled photons here and 2 entangled photons here. You measure the inner 2 photons and then the outer 2 photons become entangled. It's the same idea, but now with spins. So you do a joint measurement of the state of the two photons, and depending on the outcome of that measurement, if you get a particular outcome, that's so-called heralded entanglement. And so this was demonstrated back in 2013 by the Hansen group in Delft. And so it was a very impressive experiment published in Nature, and it's very hard to do because both of these have to be cooled down in separate cryostats, and the photons have to come out, and it's a difficult experiment to do. But then they did one better just a couple years later, and they put the two cryostats with their diamond on opposite sides of the campus, 1.3 kilometers apart, and were able to entangle them by doing this joint measurement of the photons somewhere in between. And in doing so, they were able to sort of do one of these loophole-free tests of Bell's inequalities to demonstrate, that there is no causal communication possible between the two spins when you measure them. This is sort of though these authors were not part of the Nobel Prize that was given a couple years ago in physics. This is very along those same lines. And there were a lot of headlines about this at the time when this came out, about this loophole closing. So these experiments are very impressive, and they're, like I said, they're difficult. You do have to cool the system down. They don't work at room temperature. And this sort of heralded experiment means you have to run the experiment many, many times, emit many, many photons before you get an entanglement. And so it's not like exactly what you want for like a quantum computing system where you want reliable entanglement every single time. Although it does have possible applications for things like quantum networking, where you want to be able to transduce quantum information from a physical a stationary qubit system into these flying qubits and remotely entangle your remote systems. Okay, so that's one method for entangling NV spins. The other method is a little bit more, you'll see, sort of at least seemingly amenable to scaling this up on a chip. And the idea is just that these are spins, and like I said, they have a magnetic moment that produces a field. And so if you want them to interact, you should just be able to bring them very close to each other, and neighboring spins should feel each other's dipole field. And it turns out that if you want to have the field strong enough to have an effect that you can measure within the coherence time of the spin state, like which is sort of on the scale of maybe a millisecond, you want them to be on the scale of, say, 10 nanometers apart. And this has been demonstrated. And so this is also from 2013, room temperature entanglement between single defect spins and diamond. And so they literally just found two NVs that were very close to each other, and by manipulating their states, they could see that they had this dipole-dipole interaction that led to the generation of entangled states. And so it works, but it's still challenging. Some of the challenges are that, now I said these spins are very close to each other, 5 nanometers apart. So how do you individually address them? You could imagine if you want to have a computing system, you're going to need many qubits that are similarly closely spaced. And that becomes even more challenging to think about how are you going to read out one of these spins at will, or manipulate one of them at will, when your laser spot is like hundreds of nanometers and is covering many, many of them. So we want good resolution. Additional challenges that I won't have time to talk about today include how do you reliably place these defects so close to each other, right where you want them, and also how do you turn the coupling on and off so that you can perform like a 2-qubit gate operation as opposed to just having continuous coupling. And there are ways that I think you can do that, but I'm going to focus on the addressability here. So the approach that we are taking to doing this is essentially the idea of being able to control the magnetic environment of these qubits with a very high spatial resolution and very high time precision. And the reason we need to do that, very loosely speaking, is that in normal electronics, or for that matter, say charge-based quantum electronics like superconducting qubits, what you want to be able to do is move an electron from place to place. How do we do that? That's what it looks like. Okay, there's an animation of an electron moving. How do you move an electron? You apply a voltage, you apply an electric field. And so that's pretty easy to do. But if you have spins, what you want to do is you want to not move the electron, you want to flip the spin state. You want to manipulate the spin state. And so, like I said, to move it, use an electric field, which you know very well how to scale down, to put on a chip, to scale it down to nanometer length scales, to turn those voltages on and off on nanosecond time scales. We do all those things in silicon electronics, and we can do those things in charge-based quantum systems as well. But these things, all these things are not easy to do with magnetic fields. And the approach that we're taking to doing that is to engineer a magnetic system that can produce magnetic fields on very short length scales that could be manipulated on fast time scales. And so this is a simulation of a magnetic vortex and the magnetic field it produces. And that's sort of the system we've been studying to try to solve some of these problems. So the sort of idea of a magnetic environment is there's sort of a couple of things to consider. One is you have a magnet, it produces a field outside of it. Obviously, a bar magnet, produces a dipole-like field. Anytime you have magnetization pointing out of a surface, you get some field outside of the magnet that will interact with nearby spins. You can also have dynamics of a magnet, though. So magnetic waves called magnons or spin waves that are sort of a wave in the magnetization that often are sort of at gigahertz frequencies. And so we can think about using those dynamic magnetization features as well as a way to interface with spin qubits. And here's just a few proposals of how you might interface magnetic elements with these spin qubits. So here's a theory paper where we have an NV center in diamond and a ferromagnet, and it allows you to sort of enhance or control the nearby spin by locally amplifying fields that you're applying. Addressability of spins. If you have a magnetic field gradient, then you'll be applying a different magnetic field to different nearby spins. And so this is an experimental paper where they have a very small magnetic tip that produces a very strong magnetic field gradient near the spins that allows you to address them. And here's another theory paper for controlled coupling actually enabled by magnons. So instead of bringing them close together spatially, like I was talking about, here they can be still kind of far apart, but this magnetic system in between effectively couples them via magnons that are exchanged from one side of that magnet to another. Okay, so like I said, we're looking at these magnetic vortices. So for example, here, well, I'll come back to it. So the idea is, engineering magnetic systems, instead of creating a physical shape like a scanning tip or something, can you get the magnetization itself to have this nanoscale field producing properties? And so we look at things like vortex. You can create a domain wall in a thin strip of a magnetic material that has this vortex domain wall where the magnetization changes direction. You can have a magnetic disk that forms a vortex with a core at the center of the disk, or these bubble domains. The bubble domains were actually, it's not a new thing, that's an old thing that they actually made memory devices out of back in, I think, the 60s or the 70s, but that don't work as well as today's memory, so we don't use them anymore. And more, there's things like skyrmions, where essentially vortex-like structures that form naturally in material. And so there's lots of proposals for how you can use these things for memory devices, logic, sensing devices, even in the classical domain, as well as for addressing and controlling spin qubits. Okay, so like I was saying, we need to control these nearby spin qubits. And one good way to do it is using a field gradient. So if you have a field gradient, then nearby spins experience a different field. They have different splittings, and they will have different frequencies. They'll respond to different frequencies when you apply fields. So how much of a gradient do we need? Well, if we want, say, a 20 megahertz difference, so remember, these frequencies are usually gigahertz scale. So megahertz is a small but not too small frequency difference. You would need a gradient on the order of something like on the scale of millitesla per nanometer. And that is in fact the kind of gradient you can get with a sharp magnetic tip, just like I was showing was demonstrated in that previous paper. Now, the disadvantage of that is that it's not really scalable. You have one tip, it moves, it's a physical thing, you actually physically move it. It's slow, it requires all these piezo elements to move it around. And so we want something that's integrated and you can scan quickly, which leads us to this sort of idea of a magnetic vortex, which at the core, that very central point, produces this very strong field that gives us the same kind of field gradients. And it turns out that by applying a global field to the whole system, you can move where the vortex, I'm going to skip this, you can choose where the vortex core is within the material. So here I'm sweeping a sort of a small magnetic field to the whole system, and it moves this vortex core around. And it turns out you can actually move it very quickly on sort of nanosecond timescales, maybe tens of nanosecond timescales. Okay, it also has dynamic properties like magnons and spin waves that we can both detect and try to exploit for control spins. So I'll kind of very quickly go through the kinds of experiments that we're doing. I won't really fully explain them, but I'll give you the flavor of it. So we build samples where we fabricate these magnetic disks that host magnetic vortices. And then we either can put diamond nanoparticles that host NV centers on top of those disks, or we can fabricate the disks directly onto a diamond chip. We can do some scanning optical microscopy to measure the fluorescence from these particles. So here we see a diamond nanoparticle that has several NV centers in it, sitting on top of one of these magnetic disks. And then we do actually two different kinds of optical measurements to probe the system. We image the vortex magnetization by measuring the reflection of green light off of the magnetic material. And we also measure the fluorescence of the NV centers, so-called optically detected magnetic resonance, to probe the spins. So it's two experiments in one. And from the first experiment, we can image where the vortex is. So here's our magnetic disk, and the black spot shows you where the vortex is as we shift it using a magnetic field. And so the point is, you see that as we go from 0 to 9 millitesla applied magnetic field, the vortex is moving right past where this diamond nanoparticle is. So applying the magnetic field moves the vortex core. And okay, I'm going to skip this. We can measure actually in some detail how the vortex core moves, really down to sort of nanometer scale precision, map out where it gets stuck in defects as it moves and things like that. Okay, so now here's where we bring the vortex together with the diamond. So the experiment is we have this magnetic disk, a diamond nanoparticle is sitting on top of it, or in some cases, the whole thing is on a diamond substrate and there's NV centers right below the disk. And then we're going to sweep a magnetic field, which will move the vortex core along this path right nearby the spin qubits and then also far away from it. And then we'll measure the spin resonances of the spins as we move the vortex. So this is half of the data, the half when the vortex core is far from the NVs. And we see two different splittings because we have two different NV centers here in different orientations. And this is sort of what you expect to see, is this sort of splitting due to the increasing magnetic field that we're applying. And in the absence of the vortex core, you would expect at negative magnetic fields, you'd see exactly the same thing flipped over. But we see something quite different in the negative direction, especially right around here, where the NV centers get close to the vortex. So you see all these much larger splittings, and you see all this broadening and jumps and things like that. So these are the effects of the NV vortex interaction that we might hope to exploit for controlling the spins and for addressing them. And so we get this big splitting that occurs sort of quickly here, means that we have a large gradient, which seems to indicate that the gradient should be large enough to do this spin addressability that we want. So it opens up the possibility of having a lot of very closely spaced spins, perhaps close enough that they're coupled via their dipole-dipole interactions. And then we can illuminate them all with a green laser to initialize them and measure them, but then move this vortex core around to individually control them and individually shift their frequencies so that we can individually measure them. And so we've carried out a series of experiments to test how this might work, where we initialize the spin, move the vortex close by, move it far away, and then see, can we then go and coherently manipulate the spin? And we see that we can. And, various tests where we see what happens when we're manipulating this, moving the vortex while we're manipulating the spin and things like that. And we see that we can sort of reliably move the vortex in about 100 nanoseconds without losing the coherence of the spin state. So it opens up the possibility of doing many operations of this type within the lifetime of the NV spin. Lots of other things happen too. It's a very rich system that is interesting to study on its own. And in fact, sometimes it's interesting to think of the NV spin as a sensor here that we're using to discover things about magnetic systems. In this case, vortices, but we can apply it to other magnetic systems as well and see what's going on in the magnetic system and how that, things are manifesting on the nanoscale. And one thing we discovered here is that the fields produced by the moving vortex are themselves chiral. The vortex has a handedness to it because it's spiraling around, and the fields that occur above the vortex have a handedness as well, which means that they couple more strongly to some spin transitions than to others. And so here's a simulation of those fields right above the vortex core. And you see that they get very large and have an ellipticity to them, which drives one of the spin transitions here much more strongly than the other. I'm just kind of running through a bunch of results here. We can see how the impact of the vortex core impacts the lifetime of the spins, the coherence time. And sort of unfortunately, we see that when the vortex core is very close to the spin, it gets a dramatically reduced spin lifetime, which is unfortunate because we don't want that to happen, unless we want to think of it as using as a sensor, in which case we do want it to happen. For computing applications, we don't want a short lifetime. But we see that in some cases, the lifetime isn't that short. So we have some hope that we can get still this strong coupling, but find ways to avoid too much reduction in coherence time. And so here's some examples of mapping out the dynamics of the vortex using the NVs and seeing how they couple the different dynamic ways that the vortex changes in time, both the sort of spin waves and the motion of the vortex core. We see it occurring at different frequencies in the NV spectrum. But I just wanted to flash that up there and show some references. Okay, so I think that's all I wanted to say. I sort of wanted to give you an overview of the nitrogen vacancy platform and show you that it has applications today for nanoscale quantum sensing. These results I was talking about, though I sort of presented them through the lens of developing an architecture for computing systems, what we're also doing is we're sensing what's going on in a magnetic system. And so you can buy scanning diamond tips now from at least two companies that you can use as a quantum sensor to probe magnetic systems of various types. And as we develop these capabilities for controlling and measuring individual qubits and engineering them into systems where we can ultimately entangle them to each other, we hopefully pave the way towards computing platforms where we can really build large arrays of these in a room temperature, possibly room temperature, scalable solid state system. And one approach that we're exploring in my lab is to use magnetic systems, particularly these sort of interesting magnetic textures, to engineer the magnetic environment that can enable the nanoscale spin addressability and coupling that you need to scale up these entangled systems. And I want to acknowledge the graduate students whose work I showed, Mike Wolf, Robert Badia, and Madi Mernia, who are former students, Jeremy Trimble, a current graduate student, collaborators at University of Chicago and Argonne National Lab who make diamond samples, and our theory collaborator, Shulei Zhang. I actually really regret that I didn't update this slide to include our current NSF support in addition to DOE support as well. And so with that, I'll go back to my conclusion slide and thank you for your attention.
Well, thank you for that great talk, Professor. Now we have a little bit of time for questions. If anyone has any questions, they'd like to unmute or ask in the chat.
Yes, hello. I have a question regarding sort of just the experimentation or the process that the crystal goes through as you excite it. So I really wasn't understanding the diagram that you had in the presentation. Is the MS equals plus or minus 1? Is that like saying that it's in the spin state at a ground state?
Let me go back to it. Yeah, so the idea here is that if you just think, I guess I don't know, people have different backgrounds. So let's see, we'll try to put it in a general term. So probably most people have had, a chemistry course. And so you may remember this from chemistry. I should just find the slide. You have an electron, say, that's confined to, say, a Coulomb potential in an atom. And if you solve Schrodinger's equation, you can get, what are the orbital wave functions for that state, and you get your 1s, your 2s, your 2p, 3s, 3p, 3d. You may recall that you get the orbitals with different wave functions, but the electrons also have spin, and so you have to add to the orbital states the spin states. Spin 1/2, and the way the spin states work is that there's a total spin. There's sort of two quantum numbers that specify the spin state: the total spin and essentially the direction of the spin, the projection, of the spin onto some axis. So here's this picture again. And so in this case, it's not a spin 1/2 system, it's a spin 1 system. And the way it works is that you have your total spin, which is 1 in this case, 1 h bar. And the way it works is that the direction of the spin is quantized to be going from minus the total spin to plus the total spin in steps of 1 h bar. So a spin 1/2 goes from minus 1/2 to 1/2 because the total spin is 1/2. Spin is 1, it goes from, it can be -1, 0, or 1. And so in that lowest orbital state, in that lowest orbital wave function, there's 3 possible directions the spin can be pointing. And the same is true for the next highest orbital state, for the spin 1 state, 3 possible directions it could be pointing. Did that make sense?
Okay. Yes. But then why does the singlet state not have a spin of 1 or 1/2 or anything?
Yeah. So it's another complicated thing from quantum mechanics is so-called addition of angular momentum. So the spin is angular momentum, so if you have 2 spins, they're spin 1/2. Like I said, for 1 spin, you can have spin, spin 1/2 could be -1/2 or +1/2. If you have 2 spins, how do they add up? Turns out the total spin can either be the sum of the 2, spin 1/2, so think it's spin 1, or the total spin can be, they can be sort of opposite. And you get spins, they cancel out, and you get a total spin of 0. So that gives you your 2 possible total spins, spin 1 or spin 0. And sort of the basis where this usually is, so those are the so-called triplet and singlet states. And so when you've got the total arrangement of spin 1, this again, sort of loosely speaking, if you can see my fingers, that's sort of like 3 directions that spin 1 can point. But when they're spin 0, there's no direction. It's just 0.
I see. All right. Thank you very much.
I'm kind of giving a hand wavy explanation or finger wavy explanation of something that you spend some time deriving in a quantum mechanics course. I think I saw a question in the chat, if I can find the chat again.
Oh, yeah, I can read the question. The question in the chat is, could NV centers be connected through spin currents acting a spin torque on the localized electron spin?
Yeah, that's a very interesting question. So interaction of NV centers through spin currents via spin torque. So there is some connection there for sure. Because actually there have been some recent papers, and I sort of was writing something into a proposal recently along similar lines. In this case, more using NVs to detect spin torques or spin currents. Whether the spin current itself could couple to the NV, I'm not sure. I mean, it's challenging because the diamond itself is an insulator, and non-magnetic. So it would have to be very close to a conductor to have some sort of interaction between the spins in in say a magnetic layer or something. But I'm not sure. Tunneling magnetoresistance. I mean, so okay, there's a few different ways to sort of think about what's going on. So one thing is, could the spin affect a current traveling by? Maybe. I mean, it would probably be a small effect for a single spin on a current traveling either tunneling through or flowing past. There is also another interesting effect known as EDMR, electrically detected magnetic resonance, which is not studied very much, but it's quite interesting and only somewhat poorly understood, which is an electrical technique where you have a defect spin, say like in a semiconductor device, in say like a p-n junction, and it turns out that the current through the p-n junction depends on the spin state of the defects in the junction, and so that's also kind of related to what you're talking about. In that case, the defect itself is directly involved in the transport, where you can have recombination from the p and the n side going through the defect. And I mean, that's an interesting effect both for quantum applications, but also it gives you a much easier way to integrate this into electronic devices for like solid state sensors. I have a collaborator at NASA, Glenn here, who's working on these things for making magnetometers for space-based applications where they need robust kinds of magnetometry that operate, in harsh environments and things like that.
All right, well, thanks again, Dr. Berezovsky. And just a reminder to everyone as we go into the last week of QRISE, our submission forms will open Monday, April 8th, and all projects will be due in the submission forms by midnight Eastern on Friday, April 12th. We're looking forward to seeing how everyone's projects turn out, and good luck on this final stretch of QRISE.